Hello, and welcome to the section 4.2 lecture video. Today we're going to start talking about logarithms. So go ahead and open up your chapter 4 notes either in another window, or you can take notes on paper and pencil. But if you want to find these handouts, they're on my math lab on the handouts page, so you can follow along with what I'm doing. So here we go. So we're on page 10, and we're talking about logarithmic functions. So last time we started talking about the idea of exponential functions, and logarithms are simply the inverses of those. So this is a similar idea to positive adding numbers and subtracting numbers are inverses of each other. If you add 2 and then subtract 2, they cancel each other out. Multiplying and dividing fall under this same kind of idea. So basically a logarithm undoes an exponent. So it goes in the opposite direction. So the inverse of an exponential functions are called logarithms or logarithmic functions. So for any a greater than 0 and a not equal to 1, the logarithmic function with base a denoted f of x equals log base a of x. So this a is a subscript, which you can see in the examples down here, where y equals log base a of x when if and only if a to the y equals x. So the output of a logarithm is the input of an exponential expression. And there's two special logarithms, log base e and log base 10. This one, ln, is called the natural log. And this one is called the common logarithm. So they get special names and special notation because of their prominence in exponential work. Log base e is the natural log, which we saw, which we're going to need when we're dealing with continuous exponential growth or decay, which is what we saw when we did continuously compounded interest. And the common log is common because everything we do in modern mathematics is, or most things we do in modern mathematics are base 10. So it gets its special notation because we're doing a lot of things with 10 to a power. So the idea behind finding the indicative value for a logarithmic function is simply the idea of asking what power do you have to take the base to get the number inside. So basically I have to fill in this blank. 1/5 to the blank power equals 1 over 125. And so the answer to that question is the value of the logarithm. In this case, that is 3. 1/5 to the third power is 1 over 125. So log base 1/5 of 1 over 125 is equal to 3. Okay, so that's the idea. Now, because of this, if we take the next example, e to the what equals 0, we run into some exceptions. So the first thing to notice here is I wrote that as e to a power. So this is just using the natural log idea. The natural log of 0 is the same thing as log base e of 0. And so what number to the e to what power equals 0? Well, there is no number you can raise a number to and get 0 except for 0 itself. So this is undefined. And in fact, when we're dealing with logarithms, the number inside the logarithm, so if I did like log base a of b, b has to be greater than 0. So we can only plug positive numbers into logarithms. Okay, so the next one is log base 3 of 1. So that would be 3 to the what power equals 1. And that answer is 0. 3 to the 0 power is 1. So log base 3 of 1 equals 0. Okay. Keep going on down here. The next one is 16 to the what power equals 2. Well, here we want to take the fourth root. The fourth root of 16 is 2. So that means 1/4. So log base 16 of 2 equals 1/4. And last but not least, the natural log of e to the 9th, well, that would be e to the blank equals e to the 9th. Well, that obviously needs to be 9. So the natural log of e to the 9th is 9. So one of the rules we'll get to in the next section is that when you have a base of a logarithm and a base of the exponential, composed together like this, they cancel each other out, and you just get whatever the exponent is. Now, before I have you try the ones on the next page, let's just show you how this works on the calculator. So you can open up your Class Calc app, and we can try doing one of these. So if you go into algebra, you'll notice that it's got three options for logs. We've got log base b, and we've got ln. Log base b is the one we want to do for general logarithms. So if I wanted to do, for example, log base 16 of 2, I could do that. And notice we get 0.25, which is exactly what we said it was going to be, 1/4. So what I'd like you to do now is flip over to the next page, pause the video, and try these. First, try doing them without a graphing calculator, without the calculator, and then you can check your answer with the calculator before you start the video back up. Okay, so now that you've all had a chance to try these, let's run through the answers real quick. So log base 2 of 16, so 2 to the what power equals 16. The answer to that is 4. So log base 2 of 16 is 4. 3 to the what power equals 1 over 81. Well, the answer to that is -4. So log base 3 of 1 over 81 equals -4. Notice here, when I took 2 to the 4th power, I got an integer. Here I got a fraction. So that was the key, the thing to notice to know that this was going to be a negative. Okay. Then log of 10 to the 6th is simply log base 10 of 10 to the 6th. And as we mentioned on the last page, when the bases are the same, they cancel each other out, and this would just be 6. And that's what's going to happen for the last 3 here. So this would be log of 10 is log base 10 of 10, which is just 1. And last but not least, the natural log of e is log base e of e to the -5th, which is -5. Okay, so that's the idea of how we simplify logarithms. And once again, we looked at how to do this on a calculator. So if you're stuck on this part, feel free to use a calculator. Yeah, okay. So similar to when we did exponentials, we want to talk about logarithmic limits and graphs and see what these look like. And so if I graph the first log here on my calculator, so we go to the graphing calculator app, and we do algebra log base b of 3 of base 3 of x, and we can see the function looks like this. Okay. So if I add that to my notes here, the graph looks something like this. Okay. And so as x goes to infinity, what happens to this graph? Well, what happens is, as x is going to infinity, as x goes to infinity that way, the y's are going up forever. So that's going to be infinity. So the limit as x approaches infinity of log base 3 of x is going to be infinity. The next one is natural log. You can graph it with your calculator if you want, but I'm just gonna skip going over to that app and just show you that it looks something like very similar to the one before it. Okay. Now this time I'm doing the limit as x approaches 0 with a little positive. Remember that positive means from the right. So as I get closer and closer to 0 from the right, what's happening to the graph? Well, it's going down forever, so that would be negative infinity. Okay. And then for the last two, we'll just go ahead and do them quickly together here. The graph of this one, because the base is a fraction, we're going to have a similar thing happen that happened with exponentials, which is that you're basically going to get the reverse of when we had a number greater than 1 as our base. So it would look something like that. So as x goes to infinity, what's happening to this graph? It's going down. So that's negative infinity. And then we're doing the same graph here. So as we get close to 0 from the right, the graph goes up forever. So that would be positive infinity. So that's what the graphs of logarithms look like and how we can use them to find limits. Now, what we're most concerned with in getting ourselves ready through this class, one of the real preparations is knowing how to use this stuff. So what we want to be able to do is we want to be able to go back and forth between the two. So if you recall from the first page of the notes today, the definition said that if y equals log base a of x, if and only if, so it goes both directions, a to the y equals x. So the idea is you can take the base of a logarithm or the base of an exponential and move it to the other side of the equation and make it the base of the other operation or the other function. So for example here, this first one is the natural log of y equals 3. So that's log base e of y equals 3. So what we do is we take this e, we move it to the right-hand side, and we make it the base of the exponential. So 3 goes up into the exponent. So this becomes y, over here, notice I got rid of the log, equals e to the third. Okay. So these are not equal statements, but they are, they are, so just different ways to write the same thing. Okay, so the next one's an exponential that we want to write as a logarithm. So since it's exponential, I bring the w to the other side, and now I write that as a logarithm. So the left-hand side just becomes x plus 2 because the w is moving to the right, and the right-hand side is log base w of r. Okay, so that's the idea. So go ahead and pause the video at this point and try writing the other 4 in the other format. Okay, so now that you've had a chance to try these, let's walk through them together. So log of y is log base 10 of y equals 2. So this would be y equals 10 to the second, or 100 if they want you to simplify that. This one, take the 10 to the other side, so it's 5 equals log base 10 of w, and we always want to write log base 10 as just log. So this should be 5 equals log of w. A similar thing's going to happen here. I'm going to bring the e to the other side. So that's going to be the natural log of p equals x, right? Because log base e is the natural log. And last but not least, the b moves to the other side and becomes the base of an exponent. So q equals b to the t. Okay, so that's one thing we need to be able to do. We need to be able to write equivalent logarithmic and exponential equations. And that's fairly easy once you get the hang of it. Now, another thing we want to be able to do is we want to be able to write the inverse function. So we said logarithms and exponentials are inverses of each other. So we'd really like to be able to find those inverses. So I would highly suggest using reversing composition for this. So if you remember, let's just start out with a fairly easy one. So I'm going to start with the upper right one. So the first thing you want to do when you're doing reversing composition is you want to write the operations in the original function in the order you would do them. So in this case, the first thing I would do here is add 4 because it's inside the logarithm, and then I would do the logarithm. Okay, and they're going in this order. So then to do the inverse, we do the inverse of each one of these operations, and then we're going to do them in the reverse order, why it's called a reversing composition. So the inverse of subtracting 4 of adding 4 is subtracting 4, so that would be x minus 4, and the inverse of log of x is 10 to the x. It's the same base but an exponential instead of a logarithm. So then when I compose this together to get my final answer, I do the 10 to the x first and then I subtract 4. So this would be 10 to the x minus 4. Okay, so that's the idea. So let's go ahead and go down to bottom left now, and I'll save that really complicated one for last. So for this one, f, I start by subtracting 1, and then I do 6 to that power. So the inverse of subtracting 1 is adding 1. The inverse of 6 to a power is log base 6 of x. And this time we're going to combine from bottom up, right, when we're doing the inverse. So that's log base 6 of x plus 1. And this is especially a useful way to find inverses when there's only one operation, right? In this case, the only thing that's happening is log of x. The inverse of that is 10 to the x. So f inverse of x would just be 10 to the x. So the fewer operations there are in a problem, the less complicated this is. Okay. So now for this one, it's more complicated. There's 4 operations going on here, but as long as you do take your time and do everything in the using order of operations, you should be fine. So in this case, if I do my order of operations, I start in the exponent. And then in the exponent, we do multiplication first. So that would be 3x. Then we added 1. Then we would do the exponent, so 2 to the x. And then we would subtract 6. Okay, so there are the operations that are being performed that give you this result in this order. Multiply by 3, add 1, 2 to that power, and then x minus 6. And then to do the inverse, we do the inverse of each one of those. So 3 times x, the inverse of that is x divided by 3. Adding 1, the inverse of that is subtracting 1. 2 to a power, the inverse of that is log base 2 of x. And subtracting 6, the inverse is adding 6. And now to do the inverse, we're going to start at the bottom and work our way up. Okay, so we start with x plus 6. Then we take log base 2 of that. Notice that I'm putting everything that's already happened in parentheses. So I'm taking log base 2 because I need to add the 6 first. Then we're subtracting 1. And then we're dividing everything we've already done by 3. So everything over 3. Okay, so that's the idea of finding the inverses. So at this point, flip over to the next page, pause the video for a second, try these, and when you're ready, hit play on the video and we'll go through them. Okay, so now that you've had a chance to try these, let's run through them. So this first one, there's only one operation here. So the inverse of log base 7 of x is just 7 to the x. Same thing's happening here. There's only one operation. The inverse of 5 to the x is log base 5 of x. Then these two are a little more complicated. So in this case, the first thing we do is subtract 1, and then we do the natural log of x. The inverse of subtracting 1 is adding 1. The inverse of natural log of x is e to the x. And now we're going to do them from bottom up. So f inverse of x is e to the x plus 1. Make sure it's really clear that that plus 1 is not in the exponent, because that would be a different answer. And then the last one has a lot of operations going on. So let's go through this one. So first thing we would do here is the exponent. And inside the exponent, we've got an x minus 1. So that's the first thing we would do is subtract 1. Then after we did that, we would take 10 to the power. Then after that, we do multiplication. So 1/2 times x. And then last but not least, we would add 5. So since the original function is these operations in this order, we now do the inverse operations in the opposite order. So x minus 1's inverse is x plus 1. The inverse of 10 to the x is log of x. The inverse of 1/2 times x is 2 times x. And the inverse of x plus 5 is x minus 5. Okay, so first thing we would do for the inverse here is subtract 5. Then I need to multiply by 2, so we put the x minus 5 in parentheses and multiply by 2. Then we take the log of that, so we put everything so far in parentheses and take the log. And then last but not least, we add 1. Okay. So that's the idea for finding inverse functions. So we already knew how to do this reversing composition idea, but now we're just applying it to this new type of function. And if you remember back to the section on inverse functions, we actually talked about 2 different ways to do finding inverses. So if you want to use the switch and solve method here, you can. I'm just choosing to show you this one method because I think it's the easier way to do it. Okay, so now that we've talked about how to deal with a lot of these things, now what we want to talk about is we want to talk about how to use the one-to-one probability for logarithms to solve equations. Okay, and some of our other methods. So we're going to talk about, this is going to open a whole new toolbox of how to solve equations using this idea of logarithms. So for a greater than or equal to 0, with a not equal to 1, if log base a of x sub 1 equals log base a of x sub 2, then x sub 1 equals x sub 2. Okay. So we're going to use that to solve equations where we have multiple logarithms, like the second one here. So if you notice here, these two equations both have log base 3. So that means that their insides must equal each other. So 2 to the x, 2x must equal 24 minus x squared. And now we can solve this using the methods we've talked about for solving quadratic equations. So I would probably add x squared to both sides to get x squared plus 2x equals 24, and then subtract 24 from both sides. Okay, so that's going to be x squared plus 2x minus 24 equals 0. And now we could probably factor this. So if we look at the numbers that multiply to get 24, we've got negative 24. We get negative 1 plus 24, negative 2 plus 12, negative 3 plus 8, negative 4 plus 6. So that's 23, 10, 5, and 2. So the one that works is this last one. So this factors as x minus 4 times x plus 6. Set them both equal to 0. And solve. Okay, now one of the things you need to be careful about, if you remember back to when we were solving square root problems all the way back in chapter 1, square root problems, square roots you cannot plug negatives into. So we would get erroneous roots. Same thing can happen with problems with logarithms in them. Logarithms have to be, can only take positive numbers in them. So what you want to do is you want to make sure neither of one of these gives us a negative inside the logarithm. So 4 works out okay. We get log base 3 of 8 and log base 3 of 8. So that one works. But if you try to put negative 6 in, 2 times negative 6 is negative 12. That's negative. So that's not a solution. So when you're dealing with equations that have logarithms in there, you can get erroneous roots, just like problems we've done previously with square roots. Now the other problems in here are all going to use the square root property to find their solution. To use the definition of logarithm to solve. So for example, here I have an x inside of a logarithm. So to get rid of the logarithm, I can rewrite this as an exponential. So just move the 3 to the other side. So this would be x equals 3 to the 1/2 power, which is just x equals the square root of 3. Okay, and so that's all there is to it. Same idea here. X is in my exponent. So how do I get rid of the exponent? I move the 3 to the other side and I make it the base of a logarithm. So this would be x plus 1 equals log base 3 of 7. And then we can subtract 1 from both sides to get x equals log base 3 of 7 minus 1. And then if we wanted to, we could get an approximation for that using the calculator. So if I go into my calculator here, I can go to the scientific calculator, go to algebra, log base b, and just do log base 3 of 7 minus 1. And we get the answer there is 0.7712. So that is approximately 0.7712. And then the last one, same idea. We can move the x over to the other side and make it the base of that exponential and then solve this, which we'd use the square root property. So this would be plus or minus the square root of 18 equals x. And we can simplify that. The square root of 18 is 9 times 2. So this will be plus or minus 3 root 2 equals x. And if you remember back to the beginning of the section, the base of a logarithm can't be negative. So the only answer here is 3 root 2. Okay, so that's the idea. So you can use this idea of the one-to-one property if you have more than one logarithm in it. If you don't have more than one logarithm or exponential, you can now use the definition of logarithm to solve equations we weren't able to do before. Okay, so now go ahead, flip over to the next page, pause the video, and take a try at these. And then when you hit play, we'll go through them together. Okay, so let's go ahead and work through these together. So the first one, you want to get rid of the log, so just move the 5 to the other side. So this is x equals 5 to the third. 5 to the third is 125. Okay. Second one, you've got 2 logarithms, so you can get rid of them because they have the same base. So 4x equals x plus 6, and just solve. So subtract x So 3x equals 6, divide by 3, and x equals 2. The third one here, move the x to the other side to get rid of the logarithm. So this is 16 equals x to the fourth. And the number that when you raise it to the fourth power is 16 is 2. So x equals 2 there. And then this last one, move the 5 to the other side and make it the base of a logarithm. Then subtract 3. And then divide by -1. So we end up with x equals negative log base 5 of 12 plus 3. And then once again, if you wanted to, you could put that in your calculator to get an approximation. So negative log base 5 of 12 plus 3. And it's 1.4560. And remember, I'm using these wavy equal signs when I'm doing the decimal approximations because it's not an exact answer, it's an approximate answer. Okay, so now we can use some of these ideas we've been talking about to solve some application problems. So let's go ahead and look at those, and then we'll be done for today. So find the amount of time to the nearest day that it would take for a deposit of $1,000 to grow to $1 million at 14% compounded continuously. So the idea here is we take our formula for compounded continuous, a equals p times e to the RT, and we substitute in the information we know. So we want it to grow from $1,000 to $1 million. So a is going to be 1 million, p is going to be 1,000. Our rate is 0.14, and we don't know t. So to solve this, we first divide by 1,000 to get the exponential by itself. 1 million divided by 1,000 is 1,000, right? You can just cancel out zeros, so take out 3 zeros. Now, to get rid of the e and to get at this exponent, you use the definition of logarithm. So this will be the natural log of 1,000 equals 0.14t, and then divide by 0.14. And then we can put this in the calculator to get an approximation. So the natural log of 1,000 divided by 0.14. And that's 49.34. 3411. So t is approximately 49.3411. And then it says approximate that to the nearest day. Well, the easiest way to do that is say it's going to be 49 years and then take the fractional part to figure out how many days. So that would be 365 days times 0.3411 to get the number of days because it's a fractional part of a year. So 365 times 0.3411, 0.3411, and we get 124.5, which is 125 days. So 49 years and 125 days. Now, we could also solve the equation before plugging in the numbers for the variable 1. So like here, this tells us to solve the equation a equals p times e to the RT for r, right? We talked about how to do this in chapter 1. It means isolate the r. So to isolate the r, we would divide by p. So we get a equals e to the RT. And then to get to the exponent, we need to change this from an exponential equation into a logarithmic one. So move the e to the other side. So this is the natural log of a divided by p equals r to the t, and then to get to r, we divide by t. So the natural log of a divided by p over t equals r. And now that gives us a formula we can use to simplify these things, to run that we can just plug numbers in to find a rate. So then find the rate at which a deposit of $1,000 would double in 3 years compounded continuously. So if we start with $1,000 and we want it to double, that means we're going to end with $2,000. So this would be $2,000 over $1,000, and the time is 3 years. Now the first thing you should notice here is we simplify and we get 2 inside that natural logarithm. So did it matter where we started? No, because we doubled, and that's the result we get inside. If we had started at $1 million, it would have doubled to $2 million. When we simplified, we still would have gotten 2. So the interesting thing about exponentials is it doesn't really matter where you start. The rate and the time will be the same for whatever multiple you want to get. So if you start with $1 and you want to know how long it would take to double to $2, that's going to be the same answer as this problem. So we just do the natural log of 2 divided by 3, and it's 0.2310. So R equals 0.2310, which is 23.1%. Okay, so that's the idea. So go ahead and flip to the next page. And you can pause the video for a second and try these 2 problems, which are very similar to the ones we just did. Okay, so now that you've had a chance to try these, let's go and talk about them. So the first thing you should know, you might have noticed that could make these a little easier moving forward, is that if I have this formula and I solve it for, I could actually, if we solve it for t, it's going to be basically the same equation as here, except instead of dividing for r in this t in this step, we would divide by r. So a formula for the time it takes would be the natural log of a divided by p over the rate. So the amount of time it takes for a deposit to double from $1,000 at 8% would be t equals the natural log of 2,000 over 1,000 divided by 0.08. And once again, remember, it didn't really matter where we started. So I really could have just put what multiple I'm doing of it. Okay. And so we can go in our calculator then and do the natural log of 2 divided by 0.08. Okay, and the answer is 8.664. So t is approximately 8.664 years. And then the last one, we can use the formula we found on the previous page. So the rate equals the natural log of the starting amount, the ending amount, which is $2,540,689 over $30,000 divided by the time, which is 40 years. So the natural log of 2,540,689 divided by 30,000 divided by 40, which is 0.1110. So 11.1%. Okay. So that's the idea there. So that's how we can use logarithms to solve for r and t in this continuously compounded interest formula. We can also use this for other similar problems. Notice the population of the world doubled from 1915 to 1987, growing from 2.5 billion to 5 billion people. Using the exponential model, p equals p naught times e to the rt. Find the annual growth rate p for that period. Notice this formula looks just like the continuous compounded growth formula that we were talking about for interest, except with population. So you're really using the same formula no matter what type of continuous exponential growth or decay you're talking about. So in this case, our ending amount, so if I wanted to know the rate for that period, I could use this formula. the rate equals the natural log of P over P naught over T. Right? Because we're noticing that's the same formula that we saw before. So in this case, R would equal the natural log of 5 divided by 2.5 over the number of years, which from 1915 to 1987 is 37. Or you could just remember that if we're doubling something, it's going to be the natural log of 2. Either way, you're going to end up in this step eventually, but you could start here quicker. So we could just do the natural log of 37 divided by 2. Sorry, I got those backwards. The natural log of 2 divided by 37. And what you get is 0.0187. Or 1.87%. Okay. The next part says, although the annual growth rate has declined slightly to 1.63% annually, the population of the world is still growing at a tremendous rate. Using the initial population of 5 billion in 1987 and an annual rate of 1.63%, estimate the world population. Now, this one's not even actually asking us to use logarithms, because in this case, we want P is our answer. So we plug in our initial population, which is 5 billion, times e to the rate, which is 0.0163, and then it wants to know what the current world population is. Well, it's currently 2020, so that means it has been 33 years since 1987. Okay, so we can plug that in. And then we put in our calculator. So that would be 5 times e to the 0.1087 times 33. So the current world population should have been 9.3 billion people. But interestingly, the rate has continued to decline. So there's actually less than that today. I think the actual population is somewhere between 7.5 billion and 8 billion. Okay, so there's one more example, but it's similar to the ones we just did. So I think we'll skip over it and call it a day for this video. So just make sure you're doing your homework and assignments online. And if you have any questions, feel free to call, text, or email me, or come to my office hours.